Hi there, this is exercise 10b. Last lesson we looked at the properties of the sine and cosine graphs, sine and cos graphs, and we wrote down some standard rules to interpret how to go from one to the other and back again. And so this is looking at something similar, but now for the tangent graph. So with it like this will make sense. Okay. So we've got a couple of starters for you. The first starter says, look, type into your calculator cos 20 and sine 70, and then also do sine 25 and cos 65. And if you do that, I'll let you do it at the same time as I do it. So make sure your calculator is in degrees like mine is. You know it's in degrees because it's got a D at the top. If you've got any problems with that, you might need to email me to find out how to put it right. But I get cos 20 equal to 9396. I'll write 9396, 9397. And I'm going to type in the sine 70 as well. Sine of 70, and shock horror is exactly the same thing. So it's interesting that those two answers have ended up being the same. So I just want you to have a think about why that is. And whilst you're doing that, we'll have a look at sine 25 and cos 65 as well. Type those into your calculators and get answers for those. So hopefully you pause and you've done this, but I get sine 25 of 0.4226 and cos of 65, so I'll just prove it to myself. Oh, there's a shock, 0.4226. So basically this is what you're coming up with here. You've typed in cos 20, you typed in sine 70, you end up saying that if you got cos of 90 minus x, that's the same as what you would get if you didn't do the 90 trick and did sine instead. And likewise, if you did sine of 90 minus x, you get cos of x. So pick any number. Well, let's randomly say pick 20. Sine of, cos of 20 will be the same as sine of 70. That's really all it's saying. And then look at this. Starter 2, SOHCAHTOA. So sine x is opposite of a hypotenuse, cos x is adjacent of a hypotenuse. And all I'm asking you to do is say, well, imagine we did sine x, and we divided, because it says over here, divide by cos x. And the reason why I know it says sine x, because it says OA over h. O over h, and we're going to divide by, it says a over h, which is cos of x, so that's the a over h. And you may recall that when you divide by a fraction, you turn it upside down and multiply, but not the first one, it's the one you divide by. So I'm timesing by h over a, and you say, so well, what happens here? Well, the h's cancel. I end up with o over a, o over a, over a. Oh, that rings a bell. That's the tangent. So this is tan x. So what we end up with is that sine divided by cos, oops, I wrote it wrong, equals tan. Or sine x divided by cos x is tan x, which is something which is more useful than perhaps at first it might appear. Look, these are the graphs of the tangent graphs, the tangent function. Now, I had to do this on the other one. This is naught. This is actually 180 degrees. And this is actually 360 degrees. So it implies there's a line around here somewhere. If you just look, you'll notice that the graph doesn't actually ever touch that line. It gets close to it. And it gets close to it up here as well, but it doesn't really ever. That line, it's called an asymptote, is at 90 degrees. This, by the way, carries on doing something similar over here in the same way as it did for the sine and cos graphs. But there's another asymptote here, and it goes all the way down, and allow for my slightly dodgy line. Hopefully that won't touch what it nearly does, but not quite. And that's at 270 degrees. So you get these very, very definitely parts of the graph which don't join together, and either side of that you get, one's at the top, one's at the bottom, then it goes up to the top, and then it goes up to the bottom. And those lines, these places where it happens, are called asymptotes. And they're interesting for that reason. So that's the tan graph, and we've got a cast diagram there as well, which I'll come back to later. So the properties of the tan graph, well, we saw this with the sine and cos as well. So if I pick a point, now 45 gives us a great answer. Tan of 45, type in your calculator, it's exactly 1. It's a really useful answer. So tan of 45. Now what happens if I add on? So this one says add on 180. So add on 180, I get 225. Where's 225? Well, it's actually, if you do it there, and you'll notice that it's exactly the same height as tan of 45, so it's still 1. So that's why this is saying tan of x plus 180. If you add 180 on, it stays the same. The graph just repeats itself every 180 degrees, you see. If you add 360 on for the same reason, it'll just, that's another 180, that's another 180. You'll find it's still equal to 1 over there. So these two are obvious. Less obvious from this graph is this, but if you do tan of minus 45 there, it actually equals minus 1. So the tan of minus x, if you do a negative angle, you get a negative answer. Now that's the same as sine, but it's not the same for cos. And there's this other one as well, which I've put in there, tan of 180 minus x is minus tan x. Now this facet here makes it called an odd function. And sine is also an odd function, but cos isn't. In fact, cos is called an even function. But we'll come to reasons why they're odd and even later. It's just useful to know the name. It's called an odd function whenever that happens. So properties of these. Well, last time we did properties of sine and cos graph, we talked about their amplitude. And we talked about their period. Now, you can't really talk about the amplitude. Amplitude, if you remember, is how high it went compared to the middle point. The middle point's at 0, but it goes on forever. So for that reason, we just talk about its period. Its period, it repeats itself every 180. So from there to there to there, every time it gets back to there, it's repeating itself 180 degrees. And you could talk about the position of the asymptote, for instance, or what we call the point of inflection. Now, again, you could describe this in a variety of different ways. This point of inflection is this point where it kind of thinks about turn, and then it goes, nah, I can't be bothered. And so this is called a point of inflection. It's a point where it half turns but then carries on. So the point of inflection, the first one is actually at 180. I suppose you could say that's a point of inflection as well. And that's a point of inflection. So where you call the first one is up for debate. So if we look at a specific graph here, I've got y equals tan of 2x. Now, if y equals tan of 2x, you've got to think to yourself, well, what's gone on here? Well, you should by now know that this is it's actually been stretched. It's been stretched parallel to the x-axis, basically because it's almost in brackets, that really, parallel to the x-axis. And if you stretch it by that way, because it's in brackets, you should by now know its scale factor of a half. It does the opposite of what you kind of expect it would. So rather than being stretched twice as wide, it goes twice as narrow. And so last time, on my last graph, I said to you there was an asymptote at 90. So that's why this time there's an asymptote at 45. And last time, we all went the wrong way. Where am I going? Last time, the first point of inflection was at 180. Before, And so this time it's at 90. Everything is half as big. Everything is half as big. So now the period is 90, rather than the asymptote being at 90 and 270, or 45 and 135. And you can see that if I picked a value here, for instance, I don't know what that value is, but whenever it's equal to 1, you can kind of say to yourself, yeah, I can see that that gives me minus 1 over there. This is the definition of an odd function. More tangent graphs. Now, here we've got y equals tan of a half x. How has this been transformed? Well, it's actually similar to tan 2x, but now it's the stretch is sort of parallel to the x-axis again, because it's in brackets, but now it's got a scale factor times 2. So rather than the asymptote being at 90, now you can see the asymptote is at 180. And then at 540. So it's twice as big, twice as wide effectively. The period now is not 180, it's 360. the asymptotes at 180 and 540, etc. And this again is an odd function. Here are some of the rules I want us to be aware of then, and use that we saw before. So it says tan of 55 is 1.43. Let's find tan of 55 would be about there, I suppose. That's 55 then. So if I go up, it doesn't see. I'm going to pretend it goes up to there. I'm going to pretend that is 1.43. It's not a perfect graph, but you get the idea. And if that's tan of 55, what happens if it's tan of minus 55? And I go over here and I think tan of minus x is minus the answer. You can kind of see that here. That's 55. Yeah, you can see that works. So my answer here is minus 1.43. Again, the answer will either be 1.43 or minus 1.43. That's what we're looking at. Now, how can I get tan of 125 from the 55? Oh, I can see. I do tan. I do 180 minus 55. That's what I reckon 125 is. Yeah, that works. So up here, which rule? Oh, it's that rule there. 180 minus it is minus it. So this will be minus 1.43 again. And what's the last one? Tan of 415. How can I go from 55 up to 415? Well, I think it's quite easy. I'm going to add on 360. I've written it the wrong way round actually, but it makes no difference. I think that is this one. It's the tan. You take your angle and you add 360 on. And notice it doesn't change. It's still equal to tan x. So I think this is not a negative now. It's just a plain old 1.43. Yeah, they're the answers. So this is what we need to be able to do. It says here, find tan 20. Well, I assume it just wants me to type it into my calculator this time. So I'm going to do it on my calculator. Tan of 20 equals 0.36. 0.36. I'm going to 364 to 3dp. I'll type in tan of 70, because it wants me to do that as well. 2.747. Well, one thing you'll notice is not the same. Remember sine and cos having some strange things going on. Find tan of 15. Now, it's kind of implying there's a link here somewhere. So tan of 15, well, I get, as a decimal, when I press the decimal button, 0.268. And tan of 75, I get 3.73. 732. Well, I suppose I can add those two numbers together. I'm just looking at that in terms of the 8. And so if I add those together, plus the 0.268, I actually get an answer which is exactly equal to 4. Is that a fluke? Well, this doesn't exactly equal to 4. It looks more like 3.1-ish to me, so that's less useful. Write down a rule joining these together. Well, I think it's less obvious. Certainly, there is a rule, but on whether or not it's overly accessible to us now, I'm not convinced, because certainly when I add these together, it's not giving me something. In actual fact, it's to do with plus or minus root 3 and things like this, but I'll come to that at another point. I wouldn't worry too much about this now. One thing I do want to worry about is the cast diagram. The cast diagram I've shown you before, quadrant 1, 2, 3 and 4. And I want to think about, this by the way says cast, it just gone off the edge, hasn't it? I want to think about when the sine graph is positive. By positive I mean it's above the line. And you can see here and here it's above, but here no and no. They're both of those, they're below the line. So between 0 and 90 it's above the line. That means the sine graph, which that is positive. I'll write an S for that. And the sine graph is also, now this is the first quadrant, this is the second quadrant, this is the third, this is the fourth. So I reckon sine and sine is positive in those two places. Cos is positive in those two places. So I've got to go cos and cos. Tan is positive there and then there. Tan and tan. Now that's interesting. All three of them are there, so we write that as an A. Notice C-A-S-T, that is why it's called the cast diagram. You might think that's useless, but actually it becomes quite useful, and I'm going to use that more and more. At the moment, again, just have a look at it, a bit like the last slide, just have a look at it. I want you to have a go for me. I don't know what was wrong with question 1, but exercise 10b for me, please. Question 2 to 7.